All right, so we should see a little red light, flashing red light in the top left-hand corner of our Zoom windows, which means we are recording. And so then I will turn it over to Group 8 to share with us your design.
Thank you. I'll go ahead and share.
Okay. Yeah, if you could pull the presentation up.
Can you see just the presentation?
Yes.
Okay, thank you.
Perfect. All right. Hello, everybody. My name is Ryan Overholt. We are Group 8, and we are here to introduce you to the Curigator. Next. So our Curigator is broken down into 7 subsystems. We have the structure, which is going to support and act as insulation for our interior mechanisms. And then we have the optical culture monitoring system. This is going to allow us for our OD and FI imaging measurements to be taken. We have the gas manifold. This is going to allow for the injection and control of up to 5 different gases, as well as pressure release and the distribution of these gases throughout our system. The user interface is going to allow the user to control the interior of the system and indicate the conditions of our Curigator interior from the outside. Our climate control subsystem is going to evenly heat and cool our entire interior through copper tubing, which will be explained later. And then our liquid handling is going to use disposable type pipettes to inject and extract liquids as needed while preventing cross-contamination through individual well plates. Our shakers are going to use 2 different motors to create the 3 requested orbital shaker patterns. And so each of those 7 subsystems is shown here. So you can get an idea of what you're looking at.
The main goal of our design was to increase the efficiency of each of the processes to decrease the cost of the bioreactors both monetarily and environmentally. In our research, we discovered that many existing designs either do not offer liquid transfer capabilities or have ones that are not quite compatible. We simplified the liquid handling system to make up for these issues. And finally, many of our existing systems are costly, and our goal was to bring the customer a product that would not only be close to the budget, but cheaper long term. Next. The footprint of our design is about 1.1 by 0.74 meters, or about 3.6 by 2.4 feet, allowing it to fit on most standard lab benches. Additionally, the design reaches a maximum height of about 0.59 meters, or about 1.9 feet.
The structure is made up of 4 layers: an 11-gauge 5052 aluminum sheet metal exterior to protect the interior mechanism, 5 millimeters of styrofoam insulation to keep the exterior surface at a maximum of 50 degrees Celsius, copper tubing with cooled or heated water running within, which acts as a part of our climate control, and an 11-gauge 5052 aluminum sheet metal interior to support and hold the interior mechanism. To determine the minimum length of the insulation, a heat transfer calculation was performed, where 2 equations were created for the unknown heat flux across the surface. As the heat flux is constant through a surface, no matter what the materials the surface includes, these 2 equations were able to be set equal to each other, and the only unknown, L2, or the length of the styrofoam, was solved for and found to be 4 millimeters. It must be noted that the thickness of the styrofoam used in the design was larger than the found 4 millimeters to account for error, as well as screw heads extruding into the foam. This slide outlines the customer needs and the ways in which our design accomplished them. The main features we designed for included the lightweight of the subassembly, where the use of the 5052 aluminum ensured that it was underweight, as well as that it would be able to fit in through any door as defined by the ADA standards, where the minimum width was 0.8 by 0.8 meters. We also designed to ensure that the interior was easily accessible with a large opening, as well as that the design is appropriate in the BSL2 space, with all processes able to run in a fully enclosed system. We also designed to ensure that the insulation was thick enough to ensure that the exterior surface did not exceed 50 degrees Celsius to prevent any interference.
The user interface sits on the horizontal surface of the system and makes use of a 4x7-inch touchscreen powered by Raspberry Pi that will allow for easy and intuitive user controls. Additionally, this Raspberry Pi controls the inner workings of the design. The design also makes use of 3 LEDs to indicate to the user the conditions of the interior. The green light indicates that all is working well. The yellow light indicates that something has gone wrong, but that the system has not stopped. And the red light indicates that something has failed and all processes have stopped. Next. The customer needs for the user interface shown here show what our design meets and how we determined the need was met. Most of them were minimum requirements of being able to do this or that, or just if it had programmability, which we accomplished.
The gas manifold makes use of 6 3/8-inch normally closed solenoid valves. When electricity is passed through these, the valves are open and the gases are allowed to pass through. Otherwise, the valves are closed at all points. 5 of these valves allow for the injection of gases, and the remaining 1 allows for the release of pressure within the system. 5 sensors within the system allow the user to monitor and control the levels of each gas within. Additionally, when certain levels are set of the gases, when they dip below required levels, the sensors are able to autonomously add gas to the interior environment as needed. 2 fans at the bottom of the system circulate the gases within to ensure even mixing.
The fans chosen in this design were OTS fans that ran at 28 cubic feet per minute. In order for proper mixing, as well as no turbulence to negatively affect the other processes, the maximum velocity was determined. The Reynolds equation was used, and the Reynolds number was set at 100, just in laminar flow range, so no turbulence can be created. With the properties of air and the dimensions of the interior structure, the max velocity was calculated to be 468.98 meters per second. Thus, the fan chosen does not create turbulence and is okay for this design.
The tubing map is made up of 1/4 inch outer diameter copper refrigeration tubing that twists over the exterior of the system to heat the entirety of the system. This ensures that all the cultures receive the same levels of heating or cooling. The same fans used in the gas manifold decrease variation in temperature in the temperature within the system. The tubing map also controls the temperature of the system by having water flow throughout its entirety, which is kept in a separate reservoir that can hold approximately 8.4 liters of water and is pumped through the tubes. The tubing map also does not introduce moisture into the interior environment and thus removes the need for humidity control. Additionally, as no heated or cooled air is added to the system, there is less need to remove interior gases to release pressure, and thus small amounts of gas are needed. The system does not stretch the top and bottom of the mechanism to make room for screws securing the interior mechanisms and to prevent the tubes from being crushed by the weight of the mechanism. Next slide, please. Thank you. The climate control for the interior of the system is based on 2 main components. To heat the system, water from the reservoir is heated by an immersion heater to bring it to the proper temperature. A compressor pump then flows the water through a heat exchanger to achieve the desired temperature, and it goes into the tubing map. The water flows through and then goes back into the reservoir to be cycled through again. To ensure that the temperature will remain at 70 degrees Celsius, the heat loss of the warm water flowing through the tubes was calculated, taking into account the thermophysical properties of the copper tubes, the air, and the water. Based on this information, it would take approximately 1,982 watts of power to maintain the maximum temperature inside the structure. For this reason, the immersion heater is rated for 2,000 watts, thus ensuring the temperature will be maintained. Next slide, please. Considering that time is an essential factor in climate control, understanding exactly how long it will take for the temperature to change in the system is crucial to achieve maximum efficiency. First, heating up the water to 70 degrees Celsius will take the most time, since a large amount of water is being stored in the reservoir. Although it is capable of holding 8.4 liters of water, a maximum of 7.5 liters will be considered due to weight and the amount of water the tubing map can actually hold. Assuming an initial temperature of 25 Celsius and the 2000 watt immersion heater, it will take approximately 706 seconds or roughly 11¾ minutes to heat the water before it flows through the system. Once the tubing map has water flowing through it and taking considerations of the properties of air and the volume of the interior of the structure, it takes roughly 11 seconds to heat the interior, giving a total of approximately 11.95 minutes to reach maximum temperature of the interior. Next slide. To cool the system, refrigerant 1234YF will go through a refrigeration loop to bring the temperature of the water down to 4 degrees Celsius. The refrigerant will be pumped through an expansion valve to bring down the pressure of the liquid, so when it flows to the cooling plates, it will come off as a gas. When the cooled refrigerant gets pumped through into the fan, it will become a liquid again that will then flow into a heat exchanger. This will bring down the temperature of the water to whatever temperature is desired, to which the refrigerant will flow back into its respective reservoir, and then the cycle repeats itself. Next slide. To make sure that the lowest temperature necessary is maintained, the heat sink was determined. Based on the use of 20 fins on the cooling plates, approximately 39 watts of power dissipates throughout the cooling system, which can be easily maintained to keep the system steady at such low temperatures. Next slide. And then here are some of the metrics that were given, that were determined from the customer needs. Some of the needs to consider are the independent environmental conditions and the fully enclosed compartments. So, and with the interior structure on the back of it, there's like a little compartment that we keep the climate control system in. So that way it doesn't interfere with the interior or any of the other subsystems of the structure. Also to consider is to maintain internal temperature and uniform heating cooling. Those are both achieved using the tubing map. So that way it's uniform heating, and because there's no humidity control necessary, it also mitigates condensation. On the next slide.
Okay, so here we have our liquid handling system. Our liquid handling subsystem consists of 2 main subassemblies. The first of which is going to be the linear framework. The second of which is our pipetting system. So our linear framework assembly is going to include 2 belt drives. Each of these is powered by a NEMA 23 step motor, and then with stainless steel rods affixed to each belt to ensure stability and precision. So as these belt drives move in either direction, our pipette assembly is going to move accordingly along the belts in the X and Y directions. The pipette assembly can be seen mounted at the intersection between these 2 rods here on our slide. We also included a tensioner system to ensure that the belt remains tight during constant use. Next slide, please. So here, this is just kind of a close-up and an exploded view of our pipette assembly. So our vertical motion was controlled using a microlinear actuator. Here it is shown in the retracted position, but it is capable of extending up to 100 centimeters as needed during use to reach individual wells. And we included disposable polypropylene tips to ensure that no cross-contamination is minimized between individual wells, and to take care of waste using our pipette replacement system. So as the shaft, we also have a piezo linear actuator. This can be seen connected to the pipette tip. And so as the shaft of this actuator is retracted or extended, liquid will either be aspirated or dispensed from our pipette assembly. Next slide, please. Here we were calculating the pressure needed to aspirate liquid into our pipette tip, and we used Bernoulli's principles. And so we confirmed that a lower pressure than atmospheric pressure will be required to create a vacuum that will suck up our liquid into the pipette tip. Next slide, please. We also calculated the maximum linear speed of our belt drives. This was done by calculating the circumference of our timing pulleys and multiplying that by our maximum rotational speed for the NEMA 23 motors, which was 2,250 RPM. This came out to be 2.286 meters per second, or 2,286 millimeters per second. We also found the range at which we can dispense liquid from our pipette. That's going to be 1,000 to 1,270 microliters per second. We did this using continuity and finding the value for the speed at the very tip of our assembly, and then plugging that back in to find the volumetric flow rate. Next slide, please. So here we have our pipette replacement system. This is going to use 4 cylinders shown on the left here, each loaded with a spring with a hollow cylinder sitting within. And within each of these hollow cylinders, we're going to have multiple disposable tips stacked on each other. And the spring is used to create a press fit between the piezo shaft and the tip without placing too much pressure on either component, preventing any damage to the system. And then our disposal system, seen on the right, uses a set of claws that are going to deform around the pipette tip when the pipette is lowered between them. The claws are going to deform until the ridge on the disposable pipette tip breaches these claws, and then it will be raised, effectively popping the pipette tip off and into the wastebasket to be removed later. Here we have our fluid vessels. These are going to be seated within the interior, and one is going to contain our fresh culture, which is going to be aspirated and then dispensed into each individual well. And the other is going to contain bleach to neutralize any waste that we need to get rid of. And these are also equipped with our flex caps, which will be talked about later. So here are customer needs and how we address them. Some of the main ones we addressed that we just talked about are going to be the no cross-contamination. So we used our disposable pipette tips to ensure that liquids aren't mixing in those, as well as our flex caps, which will be seen later, reduce any cross-contamination between individual wells. Another one would be our waste disposal system. That was just shown using the claw to remove the pipette tip. And then our dispense rates, we have actually a range wider than was requested, but the 225 to 300 microliters per second is well within our estimated range for dispensing rates. Next slide, please.
So here is our ODFI monitoring system. There's 3 components in our system. We have the FI sensor, the OD sensor, the mounting brackets, and then lastly being our universal lighting plate. Here you can see that the ODFI sensors are both mounted onto the liquid handling mount seen before in Ryan's presentation. The width of it is 16.8 centimeters wide, making it relatively small and able to move around in the X, Y, Z direction using the liquid handling device. We have our FI sensor angled at a 45-degree angle, just so the refraction of the emitted light from the cell cultures will be refracted at an angle towards the sensor, and so the sensor can get as much emission as possible. One of our components is the lighting plate, and here you can see the dimensions of the lighting plate being 0.88 centimeters as well as 12.8 centimeters wide. The key feature of our lighting plate is that it's an LED array emitting at 630 nanometers. This lighting plate array fits up to all the well plates, universal well plate sizes, from the 96 well plate to the 386 well plates as well. It will be placed on top of the shaker platform and screwed in for when it shakes, it won't get loose. And it emits light through the bottom of the well plates or the testing tubes. Now, to ensure that we're not killing any of the cell cultures, we have to find out the maximum power emitted from the lighting plate itself. Using the emission light formula, we were able to find setting the intensity at 2 kilowatts per centimeter squared. We were able to find the maximum power, which was 4.54 kilowatts. And our lighting plate does not emit that much. It only emits a fraction of that. So we are actually in range without killing any of the cell cultures. And here's just a list of our customer needs with what we addressed them with. A key need is that processing time. We actually had our processing time at 4.5 minutes, and which is underneath the time that was wanted or maximized as.
The Corrugator also has 2 shakers available for use inside the complete system. The shakers use 2 NEMA 17 motors that use reciprocating motion to convert the rotational motion of the motors into linear motion along 2 ball bearing railways in 2 orthogonal directions. These ball bearing carriages are also lubricated with a lithium grease that offers high values of shear stability and thermal resistance to allow for long-term use of the shakers without wear. To further ensure this smooth motion, ball joints and a ball bearing track are also used for the motor attachments to the carriages, which provide the motion of the shakers. It's not shown in this image, you'll see in the next slide, but there are 2 separate attachments to mount both well plates and conical tubes to the shaker in a position that allows for OD and FI measurements with the lighting plate that's mounted directly to the top of the shaker, which would be underneath the well plates and conical tubes. The shakers are capable of 3 distinct patterns: linear, orbital, and double orbital, with a 24 millimeter orbit diameter and 150 to 600 RPM orbit speed, which falls in the range of other typical commercial shakers systems. Next slide, please. To model the shake pattern of the shaker, we solve this for this dynamic equation of motion. This demonstrates the reciprocating motion of the 2 motors in a sine wave dependent formula, which is dependent on the motor angle and the magnitude of the output motion. In this equation, A represents the amplitude of the sine wave, which was 24 millimeters for the diameter in the last slide, and the angular velocities of the 2 motors with respect to time. The shaker patterns are achieved by the 2 motors. When only one motor is running, a linear pattern is achieved as it moves back and forth across one railway. When both motors are running at the same speed, a orbital pattern is formed. And when one motor is running at twice the speed as the other motor, a double orbital pattern is made. Additionally, to ensure that the motors actually have the minimum required torque to effectively move the ball bearing carriages. Analysis of the bottom carriage under max loading conditions was done just to see if our motors would work in this system. So assuming a conical tube shaker is attached to a conical tube holder is attached to this shaker with 20 50 milliliter conical tubes, it comes out to a maximum load of 3.936 kilograms with addition of all the extra components under. So on the ball bearing carriages with a lithium grease lubrication, the minimum tangential force to move the carriages along the railway came out to only 0.38 newtons with a factor of safety of 2.0. And then when considering the ball bearing connection and the most unsatisfactory angle of the motor in the shaking motion, a minimum torque of only 4.56 Newton millimeter was required to effectively move the shakers, and the NEMA 17 motors used run at 50 Newton millimeters, so the motor torque is sufficient for these designs. Next slide. Here's just the mapping of the customer needs to our actual shaker design. So our design was able to effectively accommodate 6, 24, 48, 96, 96 deep, and 384 well plate sizes, as well as both conical tube sizes. It shakes in the 3 required patterns and has independent shaking patterns based on the 2 motors.
The flex caps are made of a shear and flexible silicone that allows for ODFI measurements to be made through with small adjustments. The silicone allows the cap to deform to fit snugly into the vessels and thus prevents any spillage during shaking. This silicone also allows the flex caps to hold their shape. The caps are designed to not be required to be removed to allow for the addition or subtraction of fluid into or out of the vessel. To add fluid, the tip of the pipette is lowered to the hole related to the desired vessel and presses into the cap, deforming it slightly. This allows for the injection of fluids without creating aerosols. To extract fluids, the pipette tip is brought into contact with the cover, and the long stems allow the system to create suction within the vessel to pull the liquid all the way out of the tube, up the stem, and into the pipetting mechanism for disposal or transfer. Small holes exist to the side of the injection and extraction holes to allow for pressure release and gas entrance. Specific flex caps may be designed in order based on the number and sizes of well plates or tubes being added to an experiment.
So the total cost of the corrugator was determined to be around $10,729.23. Most of the cost comes from OTS parts, as many of the components, such as the OD and FDI sensors, were a lot more expensive than other materials, and we can't really make those in-house. So the manufacturing costs was considering all manufacturing process were outsourced and includes all modified OTS and just raw materials that need to be manufactured to their required parts. The energy costs were based on general non-residential rates from GRU in Gainesville, and labor costs was just determined on the required pay for if one assembly worker was to manufacture all the parts in an estimated time frame.
Overall, our design can be set apart by our use of flex caps and the tubing map. Each of these help to meet the customer needs in multiple ways. Our flex caps prevent aerosols from forming and allows for both fluid addition and subtraction without the need of removal of conical tubes and well plate lids. The tubing map evenly heats the system and keeps all the vessels at the same temperature without their location being a factor. Our use of disposable pipette tips decreases the chance of cross-contamination, and our 2-motor shaker system allows for 3 smooth patterns of motion and to agitate the culture without injuring it. Ultimately, our design is simple and increase the ease of user interaction, as well as allow for the ease of assembly and repair. Next slide. Thank you to our sponsors, and thank you to our professors, Dr. Traum and Dr. Nimi, for giving us the opportunity.
We'll now take this time, if we can field anybody's questions.
Sure, this is Rick Miles with Northrop Grumman. First, let me say I really appreciate how you showed how your systems met the customer requirements after each section. I thought that was really, really good, except for when you got to the end of the presentation, you presented the cost, and I believe one of the requirements was that it cost less than $10,000, and you were over $10,000. So I'd like you to speak to that, please.
I think one thing that we could have done, or that we should do, especially for our final report, to bring our costs down, is instead of using all these OTS parts, I think there actually are some parts in there that we could probably manufacture ourselves. I think that would just reduce our costs pretty effectively. It's just about going through and picking which parts we think we can actually manufacture here ourselves.
Also,
no, I think that's a good way to address it, right? If you got a 3D printer or something like that, see which parts you could do along those lines to get it below that $10,000 cost, or you at least present an option below 10,000 and say, hey, or we could go with this, which would get things in quicker, but it's going to go above your cost threshold, right? Also, just a nitpick for me as a engineer, if you go to your liquid handling slide, there are, again, this is just about a presentation issue. Never ever, no, sorry, go forward. The slide with the figures, the numbers. Sorry. Yeah, no, one more. That one. Never present this many significant figures beyond the decimal point, right? It's just one of my little nitpicks, right? Four places past the decimal is a little overkill. Okay.
Gotcha.
And then I'll get off. The one last question I had was just any sort of vibration analysis concerned with like natural frequencies.
That's something that I don't think we have considered yet, but that's definitely something that I think we should, and we can do an analysis on. Especially with the NEMA 23 motors, we chose those for speed, but that is a very high speed. So I think there could be vibrations as well as in the shakers. That's something I think I'll definitely write a note on.
Okay, thank you.
To go a little bit more into the vibration, it's not just the vibration of the shaker table, it's the vibrations the shaker table is going to cause in everything else. So,
right, how are you isolating some of those vibrations, or if you're not isolating, how do you address it?
that's certainly something we'll consider as we continue working on this. Thank you.
So do you think some sort of damper attached to the actual shaker maybe on the bottom would be a good way to address that, or a damper for the entire system, maybe, to where it
Yeah,
attaches.
I mean, I think there's some things you can do from a mounting perspective, right? That would dampen things out pretty well. You just got to go through and look to see what might work.
Okay.
It's just something we really haven't considered. So yeah, we'll definitely take a look into that. Thank you.
Thank you.
Can you guys go back to the very beginning with that fan?
This one?
Yeah. I'm just surprised. So there were a couple of things that you said here. One, I'm surprised that you've got a speed of 500 meters per second. That's very closely, I'm pretty sure that's really close to breaking the sound barrier. If not actually over the speed of sound. Speed of sound in air. Of course, it gives it to me in miles per hour that I don't care about. I'm not bothered with unit conversions. Yeah, so 500 meters per second is really, really fast. And then you said that air at that speed isn't turbulent. And you also said that you didn't want it to be turbulent. So can you speak to why you don't want turbulent airflow in your gas manifold?
Yeah, because the location of our fans is in the enclosure of the structure. So it's circulating the air throughout the whole structure, and we don't want any turbulent fan flow. Just because I see the speed of sound. Just because, like with our liquid handling processes and everything, the shaker, we don't want to disrupt any of those things. Like any of those processes of like the liquid handling movements, or
would turbulent airflow disrupt those things? I mean, actually, if it's at Mach 1.5, it's going to disrupt everything.
Yeah.
So it's a moot point. But would having turbulent airflow actually disrupt anything?
I think it would, because of our belt system, the way our liquid handling belt system is. It could affect the tension in the belts if there's too much movement in the air.
How much air? So how much force? I mean, again, if we're at Mach 1.5, it's going to be applying a lot of force. That's crazy. But how much force does air, let's assume that air is moving slowly and that it is laminar airflow. How much force would that air actually be applying to one of these belts to disrupt the tension in it?
Hey guys, it's probably not something that would be detrimental to the system.
But you can do it. You can take your entire volume of airflow that you have, air that you have inside of it. We know that air is what, about 1 kilogram per. Is it 1 kilogram? No, it's 1 gram per meter cubed or something like that. That's not a whole lot of mass. It's really low density. So you'd be having to move it really, really fast, or concentrating and compressing it down really, really tight before you have enough inertia behind it to disrupt anything. But what are some benefits of turbulent airflow?
Mixing of the gases quicker.
Better heat transfer.
Better heat transfer.
So, yeah, but
that's something we definitely, I think, would want instead of want to prevent. I think also this calculation is probably something that needs to be reevaluated.
Yeah.
This is actually, I think, might have been overlooked. This was something that our previous group member had done. He was actually in charge of the gas manifold and dropped, I think about like 5 days ago.
Yeah.
So I think this is probably something that just got overlooked as a value. but we'll definitely reevaluate that.
Yeah,
We
please
don't
do.
want anything.
Yeah, we can also like change the focus on it instead of focusing on like the maximum speed, maybe looking into seeing like maybe if we can do more turbulent flows. If like as what you were saying, like there's not much density in air to cause like problems with our liquid handling devices or whatever.
And then as another point here, so now that I've roasted you on one thing that caught my attention right at the beginning and I was not able to let it go. Your cooling system with the pipes going through the walls, it's actually, so actual incubators, but just so everybody on the call knows this, actual incubators are water jacketed and they regulate the temperature of the entire interior of the incubator by using a mass of water that is heated and cooled appropriately. And I saw this and now I have the question, did you guys copy industrial incubators or did you come to this just by pure coincidence?
No, we didn't copy them. We started out with a sleeve that was going to be hollow, and then we ran into the problem of how we were going to move the liquid within that sleeve from point A to point B for the exit and entrance. And so we solved that problem by making it into a tubing mask.
Yeah, awesome. Yeah, I saw that and went, that's a really good idea. That's actually the way that it's actually done for incubators. So just a cool fun fact. So
Yeah, normally, oh, sorry. Normally I wouldn't chime in because I'm supposed to be the master of ceremonies here. But yeah, that for, 'cause I've seen all the designs, having been the instructor of record for the class, and we did see this morning one other very kind of clever heat transfer design. But I think this group is the only group that did like a water jacket like this. So kudos to you guys for hitting upon that solution. I think I would not have come up with the thing this morning. That was kind of a very out of the box. But I think if I were designing this is the thermal management solution that I probably would have fixated on. So good for you guys for coming up with this and having the what's the right word, the bravery to actually go through all the calculations, because it's a bit more complicated to manage this than it is some of the other we're just going to cool a little spot and blow air around type solutions that we've seen from other groups. So good job on doing the design down selection to come to this this configuration for thermal management.
Thank you.
Okay, other questions from our panelists? We've actually got this group was quick. So we've got about 12 minutes left if other people have questions.
Hi, this is Melanie with Cummins. I have a question. With the heating and cooling, do you have any type of like sensors or anything to be able to actually know what your temperatures are inside the incubator? I don't know if this is a requirement. I'm just wondering how you actually know that.
Yes, we do actually have sensors. It was just something we failed to include. The sensors for the gas manifold sit here, and the sensor for the gas sits directly underneath it. This is the gas sensors. That was just something we did not have time to include.
Okay. Thank you.
Thank you.
Okay, any final questions from our panel? I hate to pick on you, Dr. Brooks, but you're here. Maybe. Oh no. Okay, well then I'm sorry to pick on you then if you don't have sound capabilities. Okay. Any other questions? No. Okay. Well then we will wrap it up a little early then. So let me stop recording.